Oh, thank you, and I'm very happy to be here. Thank you for inviting me. My kind of plan is to talk about some of the parts of the work that are related to what I understand under this future cities and future digital universe that we are going to create. And I have taken this figure is taken from the flyer for the workshop that happened a couple months ago. So what is happening is we are envisioning systems where we're going to have a very complex, interconnected, multiple subsystems in which various devices and what I refer artificial intelligence, maybe computer information gathering, sensing, and even information exchange among humans and humans making decisions, they're going to impact all of that, impact the system. So I'm not totally sure how that's going to all work, but I'm in terms of things that we can think these days, or what's going to be needed for these envisioned future systems will be a lot of automated models for learning, gathering data, and maybe also understanding which data will be usable. And the other side has to do with the humans. We also need to understand model human behavior, and on the much larger scale, however we design them, we're also going to worry about how reliable they will be and how safe they are. All right, so that was the part that I was talking how we're going to actually have a lot of different aspects to look at from the human side, from the technical side. And what I will today go in some details is that some portions of the works that we have done maybe over the past 10 or so years that the way that seem to me relevant to what these systems may look like, and some questions that we can address within those systems. So, for example, I'm going to start. I know when it's me. I have to start with models. So we're going to look at some. The DeGroot model is one of the basic models that finds kind of it finds multiple uses for modeling actually both human behavior and also used for solving some kind of what we may think technological problems like resource allocation or scheduling tasks and things like that. So what is this underlying basic model? It was provided by DeGroot in terms of the human kind of opinion dynamic. And it's a very simple model when you may think you have M agents or M persons, and each of them has opinion. It's just a value on some topic. You can think of this PI0 is like initial opinion of a person, I, and it's something, let's say it could be easily between 0 and 1. So if you are choosing, let's say, between two options, let's say candidate A and B, then 0.5 would mean I'm indifferent. If I pick PI of 0 below, half it means I prefer A, or above I prefer B. So it's very simple model. And you can actually come up with other ways of, you can use it for ratings and recommendations as well. And then the point is that the idea is that the agents are going to interact over a graph. Graph represents who can talk to who. And then they exchange their opinion, and they have a rule they're going to follow how they mix their opinion. And the graph structure is captured, I'm writing here in a matrix W, where the entries of this matrix W, ij entry is 0 if agent J does not have a link to agent I. Otherwise, the Wij is positive, and that's basically saying when agent I receives the messages from its neighbors, it's going to decide on these weights Wij. As I mentioned, W will be capturing interaction among the agents, but W matrix also captures how much trust agents are giving to each other. In a kind of bottom line, the matrix W will be constructed on the go. Agents can do it without exchanging extra information. And in this case, the matrix is just row stochastic. And once you have that, then you can kind of set up these, put these opinions in a vector and write a simple linear dynamic here that corresponds to evolution of these opinions over time. The graph is fixed, so W is not changing. And then one can use some nice theories from Markov chain. Under right conditions, it can be shown that these opinions are gonna reach the, in the long run, they're gonna, all of these opinions are gonna agree on the one and the same value in the limit, which is I defined here by P infinity. So that's one interesting thing, but much more interesting is what is that, what is that point on which they're gonna agree? Meaning, what is this value? How do we interpret the value? So the value turns out to have some relation with some, this left eigenvector of the matrix W. And this limit is actually kind of a convex combination of initial opinions with understanding that here, I didn't write it, but here we have summation of pi I, and then opinion values, original initial values, which means that if I'm an agent I that has a very high value of this pi I probability, it's like steady state probability, it's really influence, then I'm also contributing quite a lot toward this opinion value on which we are all gonna agree. That being said, is basically pi I's are typically viewed an influence, and it's highly influenced agents will have an impact on this limiting value. That's one. Second is that by using this simple equation here and looking at how the value pi I, who's gonna have high values, you can also, from these equations come that also it has to do, of course, with the graph structure, but also has to do with the weights that are given to maybe other influential agents. Let's say pi L is also high, then actually means that if I want to be influential, it will be good for me to be connected to influential agents and also give them as much weight as I can. So we'll revisit this later from a different perspective. But in a nutshell is that this simple dynamic, what it allows us is to align the values on a single variable. However, it's not hard to see. You can extend it to vectors, so you can align decisions that are on multiple kind of topics, if you wish. You also can extend this to time varying graphs. I'm not going to go into that direction at all. It gets more complicated, but the part is that the key observation for this to work is twofold. First, every agent is honest. They are already honestly reporting their opinion. Second, they are compliant. What I mean by compliant, they really follow the rule of the mixing. They are not trying to discard the neighbors. They're not trying to kind of cheat. They are following update rule rigorously. And one last comment is that really this point on which they agree, in this case, it's just determined by the mixing matrix and initial values. But it turns out you can really steer this agreement point to serve other purposes. And let me see, okay, here it is. So one option is now you can use this DeGroot model as an underlying mechanism for aligning, let's say, a system of agents where their task is sort of different. So this is kind of on a, one can think of, maybe I have a system. Let's say I'm supplying some kind of resource, but there are multiple centers that are geographically distributed. These are kind of these nodes, and they're responsible, let's say, for supplying some resource, but they're also collaborating with each other in terms of that they will help each other if the demand in a certain area needs to be met. They will help each other kind of deliver that demand to satisfy the demand. And on a very simple, I'm saying simple because I'm here looking at the problem on a level saying, okay, these centers or entities that are delivering some good or managing resource, they have some objectives, local, actually these could be their local costs. So from the system level, they want to they'd like to minimize this unconstrained problem. I'm not bringing constraints because, again, I want to keep the story simple. You can easily implement and add constraints that are very natural, or consider them penalized and involved in these cost functions. So every of these entities here has its own objective function that is reflective of their kind of supply or ability to provide a resource. And but overall, they want to solve this optimization problem that is kind of good for everybody on a system level. However, they are not really connected all to all. They cannot put the data in one place in order to distribute, to kind of solve this problem. So the idea is to think of them, okay, they might be separated. They can communicate over some connected graph. And instead of them trying to centralize their kind of operations, they could actually run on the idea is to run some form of consensus together with something that will help them solve the problem. And what consensus or the DeGroot model here does is actually removes the role for a central computational unit for any central entity. And let's say I will not see what I'm going to do here. These are some examples of how the problems may look like. Actually, these days, these entities that we are talking may even have a lot of data collected, and the data you don't want to move the data. So you can think of, I may implement some local machine learning algorithms in these nodes to actually help me to solve some problem on a system level. And I'm going to go to model what it, excuse me, what the optimization model looks like. So if you want to solve that problem distributedly, we can now think of a simple gradient method. Suppose you are implementing it to solve your, so every agent will have some estimate xi of t at time t as an estimate of what the optimum might be for the system. And at instance t, when they communicate, exchange their decisions locally, every agent will follow up with update, which says that I will take the decisions that I receive from my neighbors, I will mix them in a DeGroot flavor, and I get this consensus step. But after that step, I will just take care of minimizing my own objective function, which is fi, and I'm really mimicking here a gradient method. And it turns out, even though this is a very simple model, this alignment, this DeGroot step here allows you to really, of course, assuming that the graph is connected, allows you to solve the original problem. And there are results, I don't want to go in technical details, but under certain assumptions, you can show that these agents' local decisions will converge to a system optimal value or vector x star. However, for this model, unlike DeGroot, where the DeGroot model relies on just row stochastic matrix W, here to avoid this influence, if you remember this pi I influence vector that can happen when you are mixing according to this opinion dynamic, here, because you want to solve the optimization problem where every agent objective is taken with the same weight, condition has one additional condition is that you have to ensure that this matrix is actually W stochastic, because you want these pi I vectors to be equal. So roughly saying, you don't want everybody should have the same level of influence. And that's one, again, technical detail that if it happens that your graph is directed, here it's hard to guarantee that that this doubly stochastic property of the W is created, because you need to run additional algorithm for that to happen. And there are other algorithms that we can use replace the DeGroot model with something else to solve the problem. And I'm not going to go in that direction because my time is rather limited. And I have here references if one is interested in that direction. Subsequently, what happened is that this simple model that we just saw suffers from it's a slow. It's slow because for that particular model, step size actually had to be diminishing in order for the method to work. So there is a subsequent development of so-called algorithms that use the tracking mechanism for tracking the gradients in the system. So what's happening is the model that we just saw that just uses the DeGroot model for mixing the decisions. It's somewhat selfish because agents are helping each other in terms of the decisions, the state X, but they are not really helping each other at all with respect to directions. So what it means in this case, if we want to speed up, you kind of need to allow agents to be aware of the fact that they are part of the system when they are also moving along their directions, or they should be aware that there is some system objective out there, and they should be tracking the gradients of that objective, not gradients of their just local, local kind of cost functions. And these equations here are really basically saying that's this is one way of doing it. So instead of using, so we are still mixing the kind of in the DeGroot fashion, the decisions X. However, every agent now has a different vector that is going to be using, and that vector is tracking this, in a way, system gradient over time. And that direction now has a particular way of updating. And meaning it looks to me like Kalman filtering in a way, because here is some mixing. It's like a current state, and I mean, this is just a mixing that mimics what the DeGroot model does for the decisions here. And this other term here is really saying I need to, in my direction that I'm going to share later with my neighbors, I need to also incorporate what's the change, what, not just the gradient, but what's exactly the change that my new decision is going to influence the direction coming as from my objective function. And then you need to subtract the old one, because that information about prior gradient is already contained in this mixing. So it looks like innovation term, this part here. And the rule here, again, I'm not going to go into too many details. Construction of this matrix C, here the agent I controls the row of the matrix I, W. But in this C is column stochastic, which tells that agent J, in this case, controls the column J. So the information exchange is slightly different here. Okay. That's about if you want to solve optimization problem. And that is actually what I skipped was there is a literature there if you want to look at convergence behavior, and there are multiple groups in which these kind of algorithms have been looked at. So that it gives you a kind of an overview of the literature. Then another thing is now to think, okay, if we can solve optimization, but what about the game? So what is in the game? In game, I may have now users, they're not necessarily helping each other, meaning they have their own costs that depend on the decisions of the others. And in this case, they are really competing. So is it possible to kind of, but they need to talk to each other. Okay, so if you look at the classical game setting, most of the approaches that are solving the problem assume that at a given time, I should be able to see the decisions of everybody in order for me to make the appropriate choice. That's kind of best for my own interest. But in some situations, so what we are trying to do here is to say, okay, now imagine one is that not all players cannot see the decisions of everybody. And that I have an example later that's very much happens in, when you are maybe having multiple markets for different things, but not all players are participating in all markets. However, what they are, their decisions are impacted, but whatever is happening in the other markets as well. So the idea here is to kind of follow this logic of DeGroot, if possible, and see if we can come up with a mechanism that can compensate for this lack of I see decisions of everybody kind of information, and see if we can solve such games with this kind of more constrained informational structure. So for the, I don't know, just a brief here, what is for the, in case of games, what do we, how the model looks like, we will have the players here now, I'm gonna call them players or agents interchangeably. Each of them has its own utility function. In my case, it's usually minimization, so it's always cost. And the player I, in this case, the payoff depends on the decisions of everybody. I'm thinking simple, you can think simple case here, xi's are just numbers. So payoff for agent I depends on the decisions of all the other players in this game. And a solution to this game is usually a Nash equilibrium, which is a point in the kind of, what is that point in the point x star, which is feasible. So it's such that if I look at the payoff for every agent I, if I look at the payoff, what that agent is making at the Nash equilibrium, that value is always at least as good as any other choice that player I can do, provided that the other players, this is the notation, the decision of the other players is fixed at the x star value. So if one agent tries to check if he can do better, it actually cannot do better than the current decision xi star for in its case. So again, of course, we're going to assume that these functions are player know that's typical in the game. Players don't reveal to each other their utility functions. So there's how do we deal now with this information? Oh, that's for some reason I have a blank slide here. It doesn't make sense, but okay. So here is this example where you can think of there are markets here. Oh, the plot is taken for Lacra's paper, and the picture is there of multiple players that are participating in about 6 or 7 markets. 6, I think. It doesn't 7. And then these arrows are showing you how the player, then we are not showing you here the graph of how the players are connected, but this just shows you how the players are kind of, when they are participating, they're gonna see the decisions. So you may think if I make these links undirected, that will create my communication graph. And then in this case, if you wanna, the situation is more complicated because now in order to kind of utilize the DeGroot model, every player, it's not just keeping track on its own decisions, like this is this big Z vector bolded here. So every player I will have this knowledge about its own decisions, but it also has to kind of have a model or estimate of what the other agents or players in the system think, or what the decision status is of the other agents. So it has to kind of account for, and this is the reason is because the payoff function here depends on these decisions of others that you don't know, you don't have access to directly. So you have to keep tracking them in order to be able to properly respond with respect to the cost you are incurring in the absence of actual knowledge of what the decisions of the other players are. And that's the actually tricky part. It makes the analysis much harder because of this tracking of all the states. Every agent tracks the states of the others. And what this at the end of the day, while you can prove, meaning it becomes more technically challenging, but one can analyze and show under right conditions that this matrix similar to conditions in the case of a kind of optimization, you can show that they can solve the game. But the cost here, the way I see it, is really, if the game is, if the number of players is large, then the state that every agent has to maintain can be really large, even if the decisions of the players are just scalars. So implementing this in a large scale can be pretty inefficient if M is really large. And alternatively, and it's fortunate for us because there are classes of games that don't really have this full dependency on the states of everybody. but they have this special class of games, so-called aggregative games, where your payoff actually, here is that toward the end, the payoff really depends on your own decision, which is XI, and not decision of every individual player, but rather on the cumulative, or actually the sum of their decisions. And this is happening in some of the, I think, resource allocation problems that can be seen actually in this, what's the name of it? The first place when it was very popular and studied had to do with the rate allocation for the wireless networks. And nowadays it found use in other places for resource sharing. Actually, Nash-Kurnot games are belonging to this particular class. And there you have a little literature. And then, so now I'm kind of closing chapter on that one. I'm thinking, okay, where else we have been seeing this model? To connect to the next topic, and I don't know, maybe I'll have to rush with that one. This is more about modeling humans' behavior when they are doing recommendations or rating. So to get to that kind of understanding, there is an interpretation of this DeGroot model from a different perspective. Actually, I'm trying here to connect quickly, but what is this really saying is, if I design a game, which is now depending on this some state P of T, then the DeGroot dynamic can be interpreted as the best response dynamic to a game where this is a payoff function for every player. So it depends on some parameter, or you can think of parameter. Cost is time varying, and this P of T vector, which is really opinion from the prior stage, affects the payoff in the next stage. And then best response dynamic will really give you the DeGroot dynamic in this case. So using this kind of simple connection, actually it was grouped with my students and postdoc. They considered something to say, can we now try to model how people are rating? Because often people are rating using some emotional feelings and not really rating certain movies and things, or giving their opinion actually as it is. So there's in their model here, they construct kind of with a slightly different change, you constructed payoff function, which is different, but it's also time dependent and depends on the average of all of the opinions that have been explicitly stated. Or this is kind of, you may think if it's a rating system, this is kind of the average of all the ratings that people have given up to certain time. And then if somebody wants to influence, actually, so why I here is your honest opinion that you have. W is this kind of historical average of what opinions have been given up to this point of all the players across from the initial time until now, when you are kind of entering. And then instead of honestly reporting, this model will actually say, if I want to manipulate this rating, I can do it. And this outcome here, it's the decision I would do to kind of change the outcome or influence the outcome the most. Let me see this down, wrong. And then again, I would say, so this basically, it goes into some direction saying that if in a certain kind of situations, we can use this game model with this, actually not as much the DeGroot dynamic here, but it's kind of coming from the point of view of the DeGroot, if interpreted in the right setting, that you can actually, there is a way to see if you want to influence something, there is a way you can do it. And I'll leave it at that. The last part, which I'm really, actually, this is something we are working these days. It's going back to the DeGroot model, because we are thinking, well, there were situations where I think in what is the blockchain that actually implements some of these mechanisms for alignment. But in a blockchain, it turns out the user might not be necessarily truthful. So what happens is now to consider if we have such models for, let's say, maybe tomorrow solving some problems, how safe these computational tools will be. And as I mentioned in the very beginning, the DeGroot model is kind of has this nice property, and we can analyze what the opinion at the end of the day is, but it assumes that the players or agents are honest, they report precisely their opinions or how they are mixing their opinions as they are evolving, and they are not manipulating. They are compliant, means they are not manipulating any of these, they are following the rule as prescribed. And now we are wondering what happens if now in such case, we go back to DeGroot, what if we have agents that are not honest, that for whatever reason, let's say they want to move this consensus point to something that is suitable for them, or maybe prevent consensus from happening altogether. And in this case, kind of we started the model where we just look at, so formally we can divide agents into legitimate and malicious. And what I mean by formally means for the purpose of analysis, we don't know. Basically, it's not needed to know who's honest, who's not. But for the purpose of modeling, we kind of separate to model the dynamic and see what is happening with the agents that are legitimate, and allow them to follow the DeGroot dynamic with only one twist now. They're not going to use a fixed values W's. They're going to time varying. Even though the connectivity graph is fixed, they're going to use time varying weights, because the weights now we're going to interpret as trust that they are giving to the neighbors. So the same rule applies for the weights, except now WLJ can be even 0, even if J is my neighbor, but WLL is never, this is XL as well. It's the way that I'm kind of, every agent gives to itself, so that value remains positive. While here now we may potentially actually shut down some of our neighbors if we have evidence that they are not legitimate, if they are malicious. We don't model malicious agents because we don't know what they can do. So their dynamic is not modeled. However, the dynamic of the legitimate agents is influenced by their behavior, because here we might be mixing with the malicious agents as well. And then you can kind of analyze the system by basically the dynamics of these legitimate agents by splitting kind of or again formally portion that comes of mixing with the actual your legitimate neighbors and those that are malicious. You put them all kind of in vector, and you get this dynamic where you're separating the behavior, not behavior, but you are looking at how the decisions of the legitimate agents evolve based on this, based on the presence of these malicious agents here. So this is really something that comes in addition to complicate this DeGroot dynamic. And then what is in this respect, what we were looking at is like to understand a couple things. One is that under which conditions these legitimate agents can reach a consensus. If we can reach the consensus, can we understand what's the bound, how much these malicious agents had pushed our consensus value with respect to the one we could have reached if they were not present. And at the end, we also want to understand at what speed this algorithm, meaning how fast we can reach that consensus point. So this is very closely related to Byzantine attack and some recent work by LeBlanc, where they are looking at, they call it resilient consensus, in which what they do is, actually the model is the same, what I just presented here, but what they are looking for is saying, their rule of dealing with these malicious agents is saying, we're gonna just, every agent will look at its own received values from the neighbors, and then I'm gonna cut some outliers. So it's gonna remove certain values and just, let's say, they just rank them from max to min, they remove certain that are at the maximum far away from according to some rule, and those that are toward the minimum also further away according to some rule, and just chop them. And then study the dynamic of this, what happens if everybody follows of these legitimate agents follows these rule, then what is happening with the consensus? Well, our approach is a bit different. We kind of assume that we'll allow agents to learn. So there are, in some situations, in certain robotic networks in particular, and this is where actually work comes with my colleagues who work in that area, they have a ways of measuring, sort of getting signal of how truthful certain, basically if I have a neighbor, there are additional signals I can collect over time that can help me kind of learn how much I should trust that neighbor. So that's the approach we take. We assume that there is additional kind of source of side information, not once that's going to tell you, oh, this neighbor is correct, malicious, so you should shut it down. But rather, it's more like hypothesis testing, and you're accumulating information, and over time, you're making decision as you go. So you may, let's say, some agent that is legitimate, you may have been misinformed, and you may have not been giving enough attention in the beginning, but as you're gathering the information, you're going to get more weight. So to kind of not go in all the technical details, but roughly saying now our W weights are actually adjusting using this actually statistical learning on a side about truthfulness. And having this side information, we have been able to analyze this model with malicious agents. I'm not going to go into there's just technical details saying, yeah, we can achieve consensus. Value on which we agree may depend on some of the initial values of the malicious agents. We measure how far that is from the true consensus and things like that. I would just kind of give you a quick plot of, I may not remember all the details, but I will in a second. So what's happening here? We have it's not a large network. We have about 45 agents, of which at one point, the picture that is given here, 30 of them are malicious, which means 15 are fair agents, legitimate agents, and 30 malicious agents. It's like twice the number of the legitimate ones. And then what we show here, there are two types of algorithms to start with. The blue, which is not really seen because it's up top here, it's covered by some other methods here. It's the method that was proposed by LeBlanc, which does this kind of outlier cutting. And it shows here a situation is where malicious agents are placing as high value to steer, as they are trying to impact as much as possible the consensus point, to move it as far as they can. So it's like, that's why we call it a maximum input attack. So it turns that there are this parameter F is related to LeBlanc's paper, but it turns out that here, these agents will achieve consensus, but they will achieve consensus that that is far away from actually the true I would say this consensus they are reaching is completely controlled by the malicious agents, and it's brought to this utmost value that malicious agents could do. Now there are several other plots here, which are all coming from our algorithm, but our algorithm here has one parameter we can control, this T0 time. So what is T0? T0 is time when we decide to start mixing. Prior to T0, we may just choose not to mix, but kind of just observe and collect signals to decide whom we can trust and how much we can trust. So T0 is kind of time when we are, so prior to T0, we can think of learning. I'm learning who's my good neighbor and who's not. At time 0, I'm confident and I'm beginning to mix the information I'm receiving based on what I learned about my neighbors. So here it shows you that if you don't spend much time learning, this is our values are going to be as kind of spiked to the up far away from or completely controlled by malicious agents as the algorithm would suffer from LeBlanc. And now, as we are just increasing slowly this delaying basically mixing, but spending more learning, one of the when we are learning, let's say for 150 iterations, and then we just run the consensus, we actually coming to we see pretty good results here in terms of we can reach really, we are not as much, this tells us that malicious agents did not manage to move us too far, actually, because they spend a good time learning and understanding, probably identifying malicious ones and cut them off so they can continue. Yeah. And that's actually the direction that we are going to investigate for few more kind of directions. But it's kind of what we are really looking is, aside from now just using these models to do some computational tasks, we are looking into possibility in their vulnerabilities, because if we are going to implement them, then kind of safety is one of the concerns. There are others who investigate privacy when they want to make sure that the information exchange among the agents is not leaking something that's that maybe a malicious user can take advantage of. But I'm not discussing, that's a different direction. I'm not discussing it. My time is up, and I want to thank you. Thank you for your attention. And if you have any questions, I'll be more than happy to answer.